Okay, in lecture number 12, let us see what is the meaning of or definition of vector triple product. Suppose we have three vectors a comma b comma c, then what do we mean by a cross b cross c? And it is given that a cross b cross c is going to be eventually be equal to a dot c times b minus c dot b times a. Okay, this is a formula that maybe is given to us. That is what eventually this vector triple product is going to be, because this is a scalar. A dot c is a scalar times vector b minus c dot b is a scalar times vector a. So what we can do is we can cross check, we can verify whether this expression is true or not, and if it is true then we can use it. Okay, now we are not getting into how somebody must have found it out for the first time. Now we are interested in applying this particular vector triple product for solving problems, and we are not going to get into details of how it has come, but we will cross check whether it is true or not. So the proof is nothing but the verification, and whenever you are doing the verification, the simplest possible situation, but still it is general, you need to consider. Therefore we will not consider three vectors I, j, k or something like that and prove this result. We have to have three general vectors. However, a can be considered as a1i, b can be considered as b1i plus b2j, and c can be considered as c1i plus c2j plus c3k. So this is going to be the general three vectors in three-dimensional space which you are using, and you have to do calculations for LHS and calculations for RHS and verify whether LHS is equal to RHS or not. This is the work which is given to students in the class, and that gives you a little better practice of dealing with cross products, the determinant solving of 3 by 3, etc. So LHS, you find out what is the meaning of LHS and what is the meaning of RHS, and you will come to know that this formula for vector triple product is true. Now what could be the variations in this? Now of course one variation is C cross A cross B is going to be opposite of this. So it is going to be equal to C dot B times A minus A dot C times B. So if you have a cross product with the cross product of two vectors, then this is what is going to be the formula, and first cross product of two vectors followed by a cross product with third, this is what is going to be the formula. Now while learning this formula itself, you are supposed to remember. How are you going to remember it? Because if we make mistake in writing this, it is going to be a mistake in finding out final answer. So the way I remember it is, this is the vector which is going inside the bracket. So first it goes to the nearest position, that makes it a dot c, and then it goes to the next position, that makes it c dot b, and whatever vector you are replacing is in the multiplication form. That is how you are supposed to remember it. Here also, first it goes to the nearest, that is c dot b times a minus a dot c times b. Okay, that is a simple trick where by which you can remember this particular expression. Okay, so once we verify this, then we give simple couple of problems just to get hang of what we are doing as far as vector triple product is concerned. Prove that I cross a cross I plus j cross a cross j plus k cross a cross k is equal to 2a. So this is the next problem that we solve in the class, which is easy, students solve it. The second problem that we give is, if a comma b comma c are unit vectors such that a cross b cross c is equal to half b, find the angle which a makes with b and c and given that B and C are not parallel vectors. So maybe let us try to solve this problem. It is given that A cross B cross C is equal to half of B, right? And the angle of A with B and C is asked. So let us apply this. I mean, this is what is there with us. So A dot C times B minus B dot A times C is equal to half B, which gives us A dot C minus half times B minus B dot A times C is equal to 0 vector. All these are vectors. Every time we have to write this bar. Right? So this is the expression that we get after simplifying the given expression, which means if I want to produce 0 vector, then this must happen and A, B, C are non-zero. Therefore B is not 0, C is not 0. Therefore this quantity should be 0. So A dot C is equal to half and B dot A is equal to 0. So if A dot C is half and A, B, C are given to be unit vectors, then the angle between vector A and C is going to be pi by 6. So theta is going to be pi by 6 here, because cos of 60 is half, and the angle between B and A is going to be, alpha is going to be 90, because their dot product is 0. That is what is a simple problem. Next problem that we give is, show that A cross B cross C. Show that A cross B cross C is equal to A cross B cross C. If this is to happen, if and only if either B is 0 or C is collinear with A or B is perpendicular to both A and C. Okay, so this is also another easy problem. 3 conditions. There are 3 conditions because of which you can achieve this. First is B is equal to 0, C is collinear with A, and third is B is perpendicular to both A and C. Again, this is simple. We don't solve it in the class. Students do it themselves. Next problem is, what is the box product of this? Because so far we had not done vector triple product, we could not have done box product of something like this, but now let us do it. This is, what is this? This is A cross B cross B cross C dot C cross A. This is what this box product is, which is equal to, first we have to resolve the cross product, figure out what it is. So maybe I use this definition. I put A dot B cross C. So I put this here multiplied by B minus B cross C dot B. I put it here multiplied by A. This is what is the meaning of vector triple product here dot C cross A, as it is, right? So this is what we want to find out. What do we mean by this? Now A dot B cross C is box ABC times B, and B cross C dot B is 0. Therefore this particular quantity is 0. This is a scalar, this is a vector, dot C cross A. B dot C cross A is A dot B cross C. Therefore this is equal to, box ABC is a scalar and this is yet another box ABC. Therefore this is equal to ABC square. So this is important identity. Box product of A cross B, B cross C and C cross A is square of box product of ABC. Right? Then let us get into applications of scalar triple product in geometry. Okay. Now this is just the introduction of scalar triple product followed by vector triple product. You have to solve several problems where this is actually to be used. However, there is no great or difficult thing that you are supposed to do. You have to remember this definition and keep working on that. Keep keeping all the rules of vector algebra that we have proved so far. If you have those rules in mind, you will not make any mistake and you will keep on getting the answers correctly. Okay, so these are some demonstrations of the problems that we are taking in the class. This has to be supported by plenty of problems, maybe hundreds of problems which you should solve at home so as to make the theory good as well as problem solving. Okay, the next is application of scalar triple product in geometry. Now we had already found out equation of a plane passing through 3 points, maybe A, B, C. We want to locate any point P. Position vectors are A, B, C and R. So at that time we had considered the linear combination of maybe we will write down what that equation was. R minus A vector, R minus A, or maybe not like that, sorry, R is equal to passing through A and T times B minus A plus K times C minus A. Two vectors are given and a point is given, right? So this was the expression that we had got as far as equation of plane passing through 3 given points is concerned. Okay, now using scalar triple product, how do we go about it? Now if we create these 3 vectors, then these 3 vectors are coplanar. That is what we want, all those p's, so that vector AP is coplanar with AB and AC. That is what is the equation of plane. So we take R minus A dot B minus A cross C minus A, and we want this box product to be 0. Volume of this parallelepiped that is formed. If this R is not in the plane of ABC, then it will create some volume. However, if it is in the plane of ABC, it will create 0 volume. So this quantity should be 0. Therefore, if we expand this, what do we get? Now this is a cross product, so let us get out of cross product first. B cross C plus A cross B, that is B cross A, opposite side, opposite AC, so plus C cross A and A cross A is 0. So this is what is the first simplification, and followed by R dot B cross C, box RBC plus box RAB plus box RCA is equal to ABC. A dot B cross C will survive, everything else will disappear because A dot A cross B is 0, A dot C cross A is also going to be 0. So this is yet another way of expressing equation of plane. R is the position vector of the point which you are looking for, coplanar with ABC, and then RBC plus RAB plus RCA is equal to ABC. This is using scalar triple product equation of plane. Now before I explain you the geometry of this, let me just check whether this and this is same or not. Now here we have these 2 vectors. Therefore, what do we do there is, let us take R dot B minus A cross C minus A. Now this is yet another very important problem solving technique in vectors which you should know. Taking dot product with some vector, taking cross product with some vector, if it reduces the entire expression because of perpendicularity or parallelity of those 2 vectors, we should think of that. Now why is dot product with B minus A cross C minus A is taken here is because in LHS this is going to happen but in RHS the B minus A cross C minus A will make both these terms 0 and only one term will survive. So that is why we have taken the dot product with this. So what is this? A dot B minus A cross C minus A. And now if you just expand this, then you are going to end up being here. This and this is exactly same, right? So the equation of the plane that we had found out earlier, linear combination, that is correct. If we learn a better tool, better technique, scalar triple product, we find out equation of plane once again and we prove that it is one and the same. Now let me show you what is the geometric interpretation of this. Let us go back to two-dimensional geometry where we have triangle ABC, and if you take any point in the plane of triangle ABC and then join them, so if I take this point R in the plane of triangle ABC, then area of triangle ABC is going to be area of RBC plus RCA plus RAB. Now here if we consider the oriented areas, then R can go out also and you can cross check if R comes out. In case of that, when we proved S minus A into R1 is equal to delta, the point was outside the triangle and still the oriented areas, if we consider, we get area of triangle ABC. Now whatever happens here in two-dimensional geometry, because of R, RAB plus RAC plus RCA is equal to ABC. Here it is happening in three-dimensional geometry, and maybe it would happen in n-dimensional geometry eventually, where we will not be able to sketch. Maybe it will be difficult, but we can sketch this and show. If we have a point in the plane of these 3 points ABC, then the volume of parallelepiped because of RBC, volume of parallelepiped because of RAB, and volume of parallelepiped because of RCA, if added together, if that becomes ABC, then R is coplanar with A, B, C. That is what is the analogy. I mean, this is two-dimensional, which we have learnt in that standard. This is three-dimensional, but the results are exactly similar. They are going to follow. Okay. Now, another interesting thing that we had done was 4 points A, B, C, D were collinear. We had found out the condition for coplanarity of 4 points, and that was x a bar plus y b bar plus z c bar plus w d bar is equal to 0, and x plus y plus z plus w is equal to 0. Then A, B, C, D are coplanar, and see, this P is D, then this is what is the condition. Now what we will do here is let us do little bit of algebra again. XA plus YB plus ZC is equal to opposite of WD if we take it to the other side, and W can be expressed as opposite of X, Y and X plus Y plus Z. So this is opposite of opposite. So X plus Y plus Z times D, and if I bring them back over here, what we get is X inside bracket A minus D plus Y inside bracket B minus D plus Z inside bracket C minus D is equal to 0. If A, B, C, D are co-planar points, then this is going to be true. Now if we take say cross product of this with B minus D cross D minus, so X A minus D dot B minus D cross C minus D, This, if we take this cross product over here, it is going to be 0, it is going to be 0, 0 multiplied by this is going to be 0, right? So this is what we have right now. And now if we expand this is scalar, x is a scalar and right hand side we have 0, so we need not have to worry about that scalar. And if we expand this now, it is indeed going to be ABC is equal to DBC plus DCA plus DAB. I mean, there is a similarity in these two. So D is a point which is becoming coplanar with this. So the condition for coplanarity of 4 points and equation of plane using scalar triple product, they also go hand in hand. That is what we have proved now. Now, and the next thing that is absolutely simple, which is to be proved, is equation of plane through a given point A with position vector small a and parallel to the given vectors B and C. So, the plane using scalar triple product, we are supposed to find out equation of plane passing through a given point A and B and C. Two vectors are given. Plane should be parallel to these vectors. So vector B cross C is going to be normal to this, and R minus A, we want it in that plane, dot B cross C is equal to 0. So R dot B cross C is equal to A dot B cross C is going to be the equation of the plane. Very, very simple. So box product RBC is equal to box product ABC. What does it mean? If you form a parallelepiped using three particular vectors A, B and C, and if you want to have origin A, B and C, then if you want to have a point coplanar, is that what I am talking about? B and C direction vectors are given and you are supposed to find the equation of plane passing through A. So this surface is going to be your plane. This is the surface which you are talking about is going to be your plane, and therefore the box product of ABC is this volume, B and C are same. Now if I have another point in this same plane but not exactly in this diagram but somewhere out, and its distance from the plane B cross C is exactly same. So anywhere if I take any point, the point is going to be coplanar if the box product of RBC equals box product of ABC. There is a geometric meaning to that also. And the next is equation of plane passing through two given points A and B whose position vectors are A, B and parallel to vector C. So this is another simple, this is the third case. We did three cases in equation of plane earlier also. Now also we can do it using scalar triple product. We can do three cases. Okay, so that is where we stop for lecture number 12, and a couple of more lectures on vectors, maybe 3 or 4, and then we have a few more lectures on coordinate geometry, 3-dimensional coordinate geometry. Then the theoretical part is going to be done. Okay, so see you in lecture number 13. Thank you.